In this video, we're going to take a look at a special type of problem referred to as an initial value problem. But before we define what an initial value problem is and then subsequently show you how to solve an initial value problem, I want to take another look at really, what these antiderivatives are. In other words, is there a way we could actually visualize, when we come up with our big f of x plus c, like what does it really look like, right? So this little intro is just a slightly different perspective on what the concept of an antiderivative is. So let's say something like this. So for f of x equals 3x squared, big F of x, which we know as the antiderivative. Again, this is the notation we're using. It's not set in stone that whenever you use the lowercase and then an uppercase, then it naturally means derivative, antiderivative. We're being consistent in this, but to make it very clear what we're doing is I'm going to say that this, so when we take the antiderivative of 3x squared with respect to x, then we come up with x cubed, right? So using our power rule, add 1, divide by the new power, that's going to give us x cubed plus c, where c can be some real constant, right? And granted, it's nice to be able to manipulate the equations and know what the equations mean, but really, what is this x cubed plus c all about, right? Well, if you think of it just purely algebraically, so we know, and if we think in terms of functions, right, we know what, for instance, the graph of x cubed, we know what that graph looks like. And then think about it, when you take a function and then you add a constant to that function, think of what effect that addition will have on the graph of the function, right? So if we keep these ideas in mind, we can actually visualize what this big f of x is, right? So let's just say graphically, right? F of x is as follows. So I'm going to, draw a pair of axes, my xy plane, right? So you got your y there, you got your x there, and let's start with just the x cubed graph, right? Now the y equals x cubed, it has this kind of shape to it, right? So this would be x cubed. Now, if I were to, since c, right, our constant of integration, essentially it's what we call an arbitrary constant, that it could be anything, right? Well, if I take c to be 1, and then think of, okay, well, what would the graph of x cubed plus 1 look like? Well, that would represent a vertical translation of y equals x cubed. So I would basically take this graph, y equals x cubed, and shift it up 1 unit. So basically there, and then it would have the exact same shape, and man, that's not too bad at all, right? And then I would have, so this would be basically my x cubed, x cubed plus 1, right? And then if I added another 1 to this one, so now if I took x cubed and did x cubed plus 2, then again, the y-intercept would now be up here, right? And then you would have, that same kind of shape up there. So then this would be your x cubed plus 2. And then if that's what it would look like if I took my constants to be positive. But what if I did like -1? So that means if c is equal to -1, then I would be taking my parent function, my x cubed function, and then translating it 1 unit down. So now the y-intercept would be here, and then the basic shape, would be something like that. So x cubed minus 1, and so forth. So I'll draw another one, -2, basically like that. And so x cubed minus 2. So what you end up getting when you refer to like the antiderivative and you use the word it's the that you're referring to is actually a set. So it's the set of antiderivatives. And in this case, what it is, they're essentially the only difference between them is a vertical translation, which algebraically corresponds to adding or subtracting a constant from your parent function. In this case, in this example, y equals x cubed. But again, it could be any big f of x, right? Whatever that function is, you can always translate a function vertically just by adding or subtracting appropriate constants. And this set of functions here, so this set of functions here is often referred to as the integral curves of f of x. So these are referred to as the integral curves of our little f of x. In other words, these are the curves that you will obtain by finding the integral or the antiderivative of 3x squared, right? So whenever you do the single process of antidifferentiation, the result is not just a single function or a single curve, but it's a set of infinitely many curves that are related by this single fact. Now, what's interesting about all of these are also called parallel curves. They're parallel in the sense that they all have the same slope. At any given point, I'll just kind of illustrate it. Let's say let's say whatever that x value is. If I drew the tangent line to each of these curves at that point, these tangent lines are all parallel. And that will be true for every value of x at which these functions are differentiable, right? So yeah, so these are, so we'll just say, they all, so parallel tangent lines, which implies that all these integral curves have the same slope, hence they're often referred to as parallel curves. So we call them, again, just another word that that's sometimes used to describe them. So these are parallel curves. But again, whether you think of them as integral curves or parallel curves, the idea is that there are infinitely many of them, right? So again, if you're working backwards, if you have, let's say you have the derivative of a function now, and you're trying to work backwards to figure out what the original function is, just by taking an antiderivative, you're not going to get one function. You're going to get, again, a set of infinitely many functions. And the idea is, how can we identify one of these? So suppose I wanted the integral curve that was like somewhere here, right? And I'm not quite sure, and let's say I know that it passes through a specific point, x0, y0, right? Then I should be able to figure out, of all of these parallel curves, which one would pass through a specific point, right? But in order for me to identify a specific one, which I've highlighted here in green or drawn here in green, I would need to know more information than just little f. I would need to know a specific point that the green curve would pass through. And that should be sufficient information for me to find its equation. Why? Because again, if these are all parallel, right, there should be one and only one function that passes through that ordered pair, right? Because again, these are all just translations of each other. So only one of them would be translated in such a way that its graph will pass through this particular ordered pair, right? And that's kind of the idea behind initial value problems. So it's the idea of we're going to know the, let's say the little f, right? Or we can refer to this as the derivative. And we're trying to figure out which of the antiderivatives now will satisfy a specific condition. And the condition in this case will be that the function would have to pass through a specific ordered pair. All right, so that's just a little bit of geometry. Again, we're not going to go very deep into this, but I just wanted to give you another way that these antiderivatives can be interpreted, right? Okay, so here, for instance, is an example. So here's I'll just list some questions and we'll go through and solve them. So a curve in the xy plane has tangent lines with slope, let's say x squared minus x plus 2, right? If the curve passes through, let's just make a point. Let's say it passes through 1, -5, right? What is its equation? So what is its equation, right? So we have a curve, right? So it's one of these curves. And we know the slope of the tangent lines. In other words, the slope of these blue lines are given by x squared minus x plus 2. And we know that the specific curve that we want, it passes through the point 1, -5. We want to find its equation, right? Well, let's see how we could turn these two or actually just this sentence. How can we set this up in the context of like antiderivatives? Well, because we know that the slope of the tangent line is the derivative, then what this is telling us is that this is the derivative of the curve. So the first sentence is telling me, again, has tangent lines with slope, so that's dy dx. And this is the slope. In other words, this is the function that gives us the slope of the tangent line, but we know that that precisely is the derivative. So here we're given the derivative of our curve, and it is x squared minus x plus 2, right? And what else do we know? We know that it says that the curve passes through the point 1, -5. Well, this is saying when x is equal to 1, the y value on this curve is -5. So we can write it like this. So y of 1 is equal to -5. So this is that extra bit of information that we're given. So this is like the ordered pair. Well, not like, it is the ordered pair on the graph, or a ordered pair, an ordered pair on the graph, and then here is the slope of the graph, right? Now we need to figure out what is the equation of this curve. Now before we actually go through it, I just want to use this example to introduce a couple terms to you, just so that you start getting familiar with them. Some of these you'll hear a lot more in more advanced courses. But notice here what we have an equation, and this equation involves a derivative, right? Because we know that the derivative of our curve, right, is x squared minus x plus 2. Anytime you have an equation that involves the derivative of a function that you don't know, because we don't know what the equation for the curve is just yet, right? That's our goal, is we're going to try to find the equation. But whenever you have an equation that involves at least one derivative of an unknown function, we call this a differential equation. Right, so we call this a differential equation, right? And you'll be studying these in a lot more detail in subsequent classes, but here we're just kind of introducing the terminology. So you have a differential equation. Over here we have a point, right, an ordered pair on the graph of this unknown function, because I don't know what y is just yet, but we're going to figure out what y is here shortly. But we have a single point, right, or a single condition that the function has to satisfy. So in addition to having this as its derivative, the function has to satisfy this equation, right? In other words, that when I plug 1 in for x, I have to get a y value of -5. And this is referred to as an initial condition. So an initial condition. And it's some condition that the original function has to satisfy, right? And when you have a differential equation, right, so something that involves a derivative, right, and you have an initial condition, and you're going to use these two things to figure out what the original function is, these two things together define what we call an initial value problem. So these two put together, when you have a differential equation and an initial condition, and you're trying to solve for the unknown function, this is what we refer to as an initial value problem. And engineering and just applied, just science in general is filled with initial value problems, and they're abbreviated IVP. And the goal of an initial value problem is to find an equation for the original function or equation or curve. So find the original function that has both of these two properties, right? So not only do we have to find a function that when we differentiate it will give us x squared minus x plus 2, but when we substitute x equals 1, it will give us a y value of -5. All right, so that's just some terminology. Now let's get into the actual solving. Well, if we have the derivative, right, and we want to go back to the original function, well, we have to find the antiderivative. So essentially, this is like our little f of x. But what we need to do is find the big f of x. So that means I'd have to find the antiderivative of x squared minus x plus 2 with respect to x, right? Again, think about it. There is a function y that when I differentiate it will give me x squared minus x plus 2. Well, if I want to figure out what y is, I have to do the inverse operation of differentiation. And in this case, it will be anti-differentiation. All right? But here's the thing. When we perform our anti-differentiation, and we can do this, right, because we have our rules now. So we're going to find the antiderivative term by term. This will give me 1/3 x cubed minus 1/2 x squared plus 2x plus c. But again, remember, when we do this, we're not just coming up with one function, but we're coming up with infinitely many curves, these parallel curves, right, that all have the same derivative. And so sometimes when you get to this step in the solution of an initial value problem, because you're finding all the possible antiderivatives that would satisfy what I have here in blue, that would satisfy the differential equation, this is sometimes referred to as the general solution. In other words, it's giving me all of the integral curves, all of those parallel curves that satisfy the differential equation part, right? If I then try to figure out, of all of these, which of them will pass through the ordered pair 1, -5, then that will pinpoint the one that I want, right? So let's now use the information here in green, and this is how I like to say it. When x is equal to 1, y is equal to -5. So what does that mean? Well, if I plug -5 in for y and 1 in for all the x's, then that's going to leave me with a really simple equation from which I can solve for c. And then once I figure out the constant, then I will know which of all of those integral curves will satisfy not just what the differential equation is saying, but also what the initial condition is saying. So let's do our little algebra. So we have -5. When I plug 1 in for x, I will have 1/3 minus 1/2 plus 2 plus c. So let's go ahead and write everything with a common denominator of 6, right? So that way our algebra or arithmetic will be a little bit easier to do. So this will be -30 over 6 minus, is equal to 2/6 minus 3/6 plus, I wrote 2/3, but this is 2/6, and then plus 12/6, and then plus c, right? So solving this for c, what do we get? So we have -30, and then I have to subtract 2, add 3, subtract 12, and then that's all over 6, and that's equal to c. So what do we have? -32 plus 3, so that's just -29 minus 12, so that's -41 over 6. So -41 over 6 is my constant. We're not going to circle this. This is just the constant. This is just a part of the solution. What we want is the equation of the curve. So we have to go back to our general solution, and wherever there is a c, replace it with the now specific constant. So we know what the constant is that will ensure that whichever of these integral curves will pass through the ordered pair 1, -5. This is the constant that will guarantee it. So therefore, here's the equation of our curve. Y is equal to 1/3 x cubed minus 1/2 x squared plus 2x, but now I know it's not just any old constant, I know the specific constant, -41 over 6. And this is what we call the particular solution to the initial value problem. So it's the specific one out of all the possible curves, which of those or which of them will pass through the given ordered pair. So we call that the particular solution, and this is what you would essentially circle as your answer. Not the constant. The constant is just one term in the equation for the curve. All right. So that's one example. Let's look at another example. Let's look at this one, and then this one I'll just write it down kind of symbolically. Suppose we know the second derivative. So let's say it is, let's say 12 square root of x plus 24x squared. That's our second derivative, right? And now let's say we know that f prime of 1 is equal to, let's say 4, and then let's say f of 0 is equal to -1, right? So actually, nope, no, not this. Yeah, let's just make it like this. F. So we know that the first derivative evaluated at 1 is 4, and then let's say the original function evaluated at 1 is -1. Here we go. So this is our initial value problem. The difference in this case, though, is that we know information about the second derivative. So we know what the second derivative is, and we have some other specific values, one for the first derivative and then one for the function. All right. Well, if we let's kind of outline what it is we need to do, right? Because if you think about it, I know how to go from a function to its first derivative to its second derivative. Assuming the function is twice differentiable, at least, I know that I can differentiate repeatedly, right? So I can differentiate repeatedly and go from a function to the first derivative to the second derivative. So that then in principle I should be able to anti-differentiate, so to go back. So if I know the second derivative, I should be able to take an antiderivative to go back to the first derivative, right? And then once I know the first derivative, do like what I did in the first example, I can go back by doing another antiderivative and go back to the original function, right? So it just, depending on how, the order of the derivative that we know, we might have to anti-differentiate multiple times. All right, so let's go back. Let's write down what the first derivative is. So that's the antiderivative of 12. Now, what I'm going to do is, as soon as I see a square root, I know I'm going to have to use a power rule for antiderivatives. So I'm going to write that as x to the 1/2, and then plus, and then I'll just have my 24x squared dx like this, right? So if I have the second derivative and I take an antiderivative, that's going to take me back to the first derivative. So let's write down what this is, and I'll just write it on the same line. So when we add 1 to this, it becomes 3/2. So this is going to be 12 times 1 over 3/2 times x to the 3/2 plus 24 times 1 over 3 times x to the 3rd power, and then plus c, and I'm going to call this c1. The reason I'm going to call this c1 is since I'm going to have to anti-differentiate twice, I'm going to come up with 2 different constants, and those constants are not necessarily the same. All right, so let's simplify what the first derivative is. So now 1 over 3/2 is the same as 2/3. So this is 2/3. So 12 times 2/3, that's 8. So I have 8 x to the 3 halves plus, and then here I get 24 divided by 3, so that's another 8, and then it's times x cubed, and then plus c1. So now this is telling me that when x is equal to 1, the first derivative, that's my f prime, that's equal to 4. So that allows me to figure out what c1 is. So let's write that down. So when x is equal to 1, f prime is equal to 4. So that gives me an equation that I can solve. So 4 is equal to, now the nice thing of having a x value of 1 is that all of these evaluate, so x raised, or 1 to the 3 halves will be 1, and then 1 to the 3rd power is 1, so I'll have 8 plus c1. So subtract 16 from both sides, and I will get, what's that, negative 12. So, yeah, so c1 has to be equal to negative 12. What does this mean? It means that here is the first derivative of the function that I don't know. I'm slowly figuring out what the function is. We started with the second derivative, and now we know what the first derivative is, and we have to repeat this process to figure out what the original function is. So minus 12, right? So we were given this, we just figured this out, and now we want the original function. That's always our goal in an initial value problem. So let's repeat the process. So f of x now is the antiderivative of this. So antiderivative of 8x to the 3 halves, and then plus 8x cubed minus 12 dx. So let's write that down. Same rules, right? We're going to use basically the same rules. So we're going to have 8 times, when I add 1 to this power, it becomes 5 halves. So 1 over 5 halves times x to the 5 halves, plus 8 times 1/4 x to the 4th, and then minus 12x plus c2, right? And then, so let's simplify this. So 1 over 5 halves is 2/5, so 2/5 times 8, so that's 16 over 5, x to the 5 halves, and then plus 2x to the 4th minus 12x plus c2. Now, let me just go back up to remind you. So we've used this condition already. Now we're going to use this condition so that when x is equal to 1, the original function value is negative 1, right? So again, we're going to do a very similar process. So when x is equal to 1, f is equal to negative 1. So negative 1 is equal to, what do we have? 16 over 5 plus 2 minus 12 plus c2. So I'm going to write everything as, well, first let me simplify this. So negative 1 is equal to 16 over 5 minus 10 plus c2. So now let's get a common denominator of 5. So negative 5 over 5 is equal to 16 over 5, negative 50 over 5 plus c2. So what do we have? Negative 5 minus 16 plus 50 all over 5, that's equal to c2. So this implies that c2 is, what's this, 29, because this is negative 21 plus 50, so this is 29 over 5. And that gives us our second constant. So here's our solution. So our function, our original function, is 16 over 5 x to the 5 halves plus 2x to the 4th minus 12x plus 29 over 5. And again, we got this by, after figuring out what the constant is, our second constant of integration, we plugged it in right into our general solution for f of x, right? So the process, this idea of solving an initial value problem, basically what it's saying, you're going to have some information. Some of that information is going to be involving a derivative or more, or not when I say more, a higher order derivative. And with repeated anti-differentiation, you can solve these simpler initial value problems, right? In more advanced courses, you're going to learn that, okay, sometimes just basic anti-differentiation doesn't work. You have to use a more involved process. But you'll get to that point. But right now, we just want to have an idea of what an initial value problem is, right? And how do we solve it using basic anti-differentiation, right? So hopefully you found that interesting, and I will see you in the next video.